Teachers, entertainers and performers.
Znovu opakuj, znovu.
Oh, sorry?
Byl problém se zvukem, zopakuj to.
Yeah, there was a...
Začátek.
Again, yeah. All right. All right, so hi guys. Welcome on the online broadcast called VIRUScience. Today we are going to focus on topic join. They are going to perform plenty of guests from all around the world, scientists, teachers, entertainers and performers. Especially I want to welcome all the viewers, all the you guys who are watching us right now. You can watch us through YouTube channel or on Facebook page, both called VIRUScience. Broadcasts VIRUScience started last winter during COVID lockdown for our local audience in the Czech Republic. For today is everything a little bit different. Today's broadcast is in English and most of our guests are joining from different countries. This broadcast is a very unique moment. For a quite long time, we all have had to perform our science shows, programs or experiments only online. Now I'm glad for this event where we can share our ideas. But now let's move to today's program. There are going to be 7 performers with experiments and questions for you, dear viewers. So don't be shy to type your answers to a comment section. And I think we can begin, and I can introduce you our performers. Here comes Chris and Diane. Yeah.
Hello.
Hi guys.
How are
Hi,
you?
hi. Hey, I'm well, and you?
Good. We're happy
Yeah,
to be
that's
here.
good. Yeah, we are happy too. Chris and Diane are both from the USA, and they are high school teachers of physics in Illinois State, if I'm right. Yeah.
That is correct.
Yes, I'm glad. So, Diane, Chris, what we are going to see from you?
Well, today we want to talk about a force that a lot of people think is bad.
But it turns out the force can be with you also.
And it can be a lot of fun.
Yeah, so that sounds really interesting. Thank you for this invitation, and see you soon.
Bye-bye.
Bye, bye for now. And our next performer is from Slovenia. Yeah, but nowadays she works as PhD student in the Physics Education Research and CERN. Lovely, Anya. Hi, Anya.
Hello.
Welcome. Yeah. I have some questions for you, but now I ask on only one of them. So what are you going to show us today?
Well, today I wanted to go with the theme join, and I want things to join at a distance. So, you know, social distancing that we have had in the last year, I want that to be seen also with a very special material that we will see more later.
Oh, okay, all right. That sounds very cool. I'm looking forward to see it. Thank you, and see you later. Other performer is from Poland, which is quite near to our Czech Republic. Here comes Tomek. Hi, Tomek.
Hello. Hi, everyone.
Hi there. You used to work in Copernic Science Center, but now you are work as science busker in Heveluše nauky. So what are you going to show us today?
As a biologist, I thought about evolution, because join is to combine more than one thing to put together. And evolution is a process in which something passes by degrees to a different stage. So I will talk about the evolution of the eye.
Oh, so that sounds great. Thank you. And now I want to welcome our next guest from Greece, Eliana. So hi, Eliana.
Hello, everyone. I'm very happy to join you tonight.
Yeah, we are happy too. So Eliana is working in Noises Science Center in Thessaloniki. Noises. Oh, sorry.
Noises Science Center.
Noises. Yeah, yes. So sorry. Noises Science Center in Thessaloniki. And your colleagues prepared a video with some experiments for today's broadcast. So what is the video about?
Well, we will do something really difficult and bizarre. We will let things fall and see what happens. But it's up with gravity and electromagnetism, and I think that it's going to be a great thing to see.
Yeah, I believe it will be amazing. So thank you, and see you in a few moments.
Yep.
And that was our last guest from abroad. Now we can move to the Czech Republic, and here comes Jaffa and Sven. Hi guys.
Hi. Hello.
Hi. I think that we can start with Jaffa. So Jaffa, you are a plasma physicist, and also you are an opera singer. Yeah.
Well, that's true.
Yeah, that's true. And you also work in Vida Science Center, as we
Obviously.
also, yeah. So what have you prepared for us today?
Well, I've prepared some joining forces in the electrochemistry field. So, what can we achieve? But just by joining forces, I want tell any more until later.
Okay, so we will see. That sounds great. And now I can move to Sven. So you are leader of program department here in VIDA. Yeah, it's right. Yeah, okay. And you are also you have also a wide range of interests. Yeah, that's also true, I think. And what's amazing, you was a former general of Moravian army.
Yeah, we had big paper shields and we threw paper balls at each other.
Yeah,
That's true.
but first go first. What are we going to see from you?
Yeah, I've prepared a sweet surprise, just a bunch of atoms to join and to release a whole lot of energy.
All right, that sounds very interesting. I'm looking forward to see it. Yeah. So thank you both guys. So dear viewers, stay with us because all performance sounds amazing. Don't be afraid to join us and write some comments into the comment section so the experiments can stand out. Our performers will be glad if they see some answers from you. So our first experiment comes from Jaffa. Yeah, just come here, guys. Yeah, you just should move the stair. Yeah, the table is here. So I already said that you are a plasma physicist and opera singer. I saw you singing last weekend, and it was great, by the way.
Yeah, thanks. Yeah, it's true. We had a performance of 2 Czech small operas from Bohuslav Martinu. It's early 20th century, so something you can hear in those, something similar to what you can hear in those Czech fairy tales, older ones.
That sounds great. But I want to ask you, what has physicist and singing in common?
Well, the acoustics, of course.
Yeah, acoustics. Yeah.
So there's a lot of feeling stuff in the singing, and you have to get into, especially when you're singing without amplification like this, you have to fill the whole house with your voice only. Then it's not really much technical aspect. There's not much of technical aspects and reasonable thinking going into it. You just have to get in there somehow.
Just feel it.
Yeah. It's a lot of trial and error.
Yeah, so thank you, but today we will be focused on electricity. Mm-hmm. Yeah, so I can think that it's enough talking and you can go on.
Much less singing in this part.
All right, so stage is yours.
Okay, thank you. Hi. So, let me start with a question. What do you think will make a good battery, or at least a battery? 2 copper electrodes immersed in sulfuric acid, or copper and zinc electrode, pair of these, immersed in tap water, ordinary tap water? Well, the sulfuric acid sounds nice. It's obviously something that we have in cars, in car batteries. But there is one slight problem. It's not really about the electrolyte of the battery. It's mostly about those electrodes. And this is why we are going to show you that the second answer is right. Here is something that we will do. As you can see, it's copper. This is zinc. And we'll try to make a zinc copper battery with tap water. But before this, we have to understand how is it possible and why am I right about being mostly focused on the electrodes? Well, let me show you. Normally, we have we are used to connecting batteries, for example, in your remote control for the TV. You actually connect one battery behind another, and this gives you increasing and increasing voltage. But what if you connect them like this? 1, 2, 3, and join these wires together. They are not behind, but they are in parallel, as they say. Well, for this we should look a little bit into how the batteries operate. And I would like to ask for the presentation, because that will help us understand a little bit. I have one. Well, there are different ways to explain how batteries work and how the chemistry works around this. And I think mostly it's because, or it comes with one solution, for example, of copper, how it reacts with the copper electrode. But for example, let's stay really in general. So may I ask for the first picture? Well, before the picture goes in, I will, okay, here it is. So, let us imagine we have some liquid with ions. We call this electrolyte. As I said, it's liquid, and there are some particles that have charge, positive charge, negative charge. In total, there is the same amount of positive and negative, probably. But what happens if we immerse one electrode inside? Well, I'd like to imagine an electrode as a monster which is hungry for those, say, electrons. It's a bit more complicated. It's a lot of quantum mechanics, and we'll just try to keep it simple by expecting that the electrodes only want electrons, so they are attracting negative. It's just a little simplification to understand. So, the electrode comes closer to the electrolyte and immerses into it. Next picture, please. Yeah. And this is where everything starts. Every metal, represented by this monster, has different appetite, different hunger for electrons. So he starts eating them away. Some of these ions wander through the liquid, end up on the surface of the electrode, and they react and they are disposed of their extra electron. And in a moment, the monster becomes stuffed, because it's a dead end. It's only a head monster. It has no stomach, it has no intestines, so there's only so much electrons that can fit inside. Well, but in case we have another monster, a different monster, different metal, then it will become stuffed because of its different hunger, a bit more perhaps. There will be bigger pressure inside. And if we connect them into a circuit, then these pressures will compete one against another. And the bigger one, of course, will overpower the other, and the current of electrons starts flowing. So that's a little bit basically how these electrodes in an electrolyte work. And the important part is that there is different sort of pressure inside each monster's mouth, but or different pressure, different hunger, but it's not the capacity. So please, the next slide. Yeah. So imagine if we had those two copper electrodes. They would have the same pressure inside, which means when they become competing together, there's no one overpowering the other one. Thus, no electric current inside, no voltage. And you can imagine that these electrodes immersed in tap water are, well, they do not provide much electricity. But in case we give them bigger mouth to amass more of these electrons, then we may do something like a parallel circuit. Instead of doing batteries separately, we will have these batteries as a bigger and bigger surface of the electrode. So, I have such configuration here. I have electrodes. You can see it's really copper, 2 plates of copper, very big surface. They are connected together, and 2 plates of zinc metal also connected together. Now, I have the canister, and of course there are some rubber pads to isolate them so that they do not touch in between. Now I will add the tap water. And we'll see, I think that's pretty much enough even. And you know what? I brought a LED diode. Normal source of light, very efficient. And I will try to actually make these 2 metals and tap water work. But for this, I need bigger voltage, because it will only give so much voltage for these 2 metals. So I brought 2 more of them. And my question for you is, how much current do you think will light up this diode? Normally, such diodes are operated by, say, 20 milliamperes. So, what do you think will be the current in this case, where we have only copper, zinc, and normal water? I will give you 4 options. 1, it will be below 1 milliampere. So even, sorry, should I start? Okay, so 1, it will be over 1 ampere. Yeah, so over 1 ampere. B, it will be exactly this operation value, 20 milliamperes. C, it will be 4 times lower, say 5 amperes. And D, it will be much lower, say under 1 milliampere. And for this, because I'm very lazy, so give your guesses, give your thoughts, and in the meantime I will connect this electric circuit together. As I'm very lazy, I will use aluminum foil instead of wires. I'll just connect. Yeah, I think this one will do. So yeah, you see I'm very lazy, so I hope it will work, of course. And I will connect our ampere meter to it as well, so that we can actually measure the magnitude of current that is flowing through the diode. I'll promise you it will light, I promise. So, plus, 2 plus, which is copper. And minus goes here. So let's first try to light the diode. It has 4 pins, meaning 3 colors are possible. And yeah, you can see there's red, a little bit of blue, and green. So what are your guesses? How many amperes will flow through this diode if it's lit like this? You can see it's quite normal light, right? It could be 20, well, it could be 1 ampere or more. Well, it could be much less. I see we have some guesses for B and D so far. I will try the green one, okay? Now, just before we know the answer, let me just tell you that this multimeter is set to show 1 milliampere throughout, so it's too little. Let's say we have 25 milliamperes so far, and this means it's 25 when it's all the way through.
Well, let's try it. Nothing happened. So it won't be 1 ampere or more. It won't be 20 probably. Okay. Does something move now? I don't think so. So it's even less, much less than 5. Now, well, it's something. So we have 1 milliampere as total, and we are about 20% inside. So we have 200 microamperes lighting at you now. So imagine that the LED diode can operate on such a wide range of currents. 1/100th of a current that you would normally use will still give you enough light. And that's everything. Thank you for your guesses.
Yeah, thank you, Jaffa.
Goodbye.
It's really amazed me. LED could work on such a less ampere, such a less current. That's great. That's great. It's amazing. So thank you very much for this experiment, and I think we can go on. Maybe my microphone not working. Yeah, we just. And we can go on. Yeah. So let's move to the next performer who comes from Poland. I just put my face mask off my face. So we move to the next performer who comes from Poland. So hi Tomek, are you the
Hello, I'm here.
Yeah, hi Tomek. Hi Tomek. Yeah.
Okay, 10 minutes is extremely short time in evolution scale. So if we want to talk about DI evolution, we will go through the main stages of this process. During workshops with children, we use this plumbing pipe as a model of an eye, so the kids can look inside of it. But you know what? It doesn't work with the camera. So I've made a new model from cardboard. This is something you can do at home. It's quite easy piece of cardboard. So here you can see first 3 stages of the evolution of the eye. Here we have just a flat surface covered with light-sensitive cells. In this model, they are just made from a baking paper, so we will be able to see the light that goes through them, like the animal would see if it was its eye. The second stage is a pocket with light-sensitive cells at the bottom. If I show it to you from the side, you can see this is the flat surface, this is the pocket, and the baking paper is over here. So it is basically the same, but we have this pocket with the cells at the bottom. And the third one here, it has the same size, but here you can see a kind of a cap that blocks part of the light. So the hole is smaller for the light to go in compared to this one. So let's test them. Let's see what would an animal see if it has an eye like this. I will shine the light from this side, of course, and you will see what an animal see on the other side. So to do that, I need to move my camera somewhere over here and put this cardboard in front of the camera. Now, Whew. First, the flat surface with the sensitive cells, with the light sensitive cells. An animal with thing like this would distinguish the light from darkness. Light and darkness. You may think that's not much, but for example, if you know where the light is and where the dark is, you can hide from predators. If you live in water, you know where the surface is because the light goes from there. Second part, the second model is this packet. And if we put the light here, we will see this shadow going on the sides. You know what? I will turn off this lamp that shines on my face. I think it will be better for us at this moment. A little bit less light, I think. All right, right. So if I know where the light comes from, I would know that, for example, a predator is moving from the side. If I see a shadow, I will know where exactly the light comes from. And the third one, the one with a cap in front. The one with a cap in front. You know what? I was showing you from the wrong side. Now, this is going to be way better. Of course it is. So, you know what? We'll go back for a second. The packet. Now you can see clearly the shadows going from the side. So you know the right direction of the light. So if something is started blocking the light from this side, I can run to the other side. Now, the third one, the one with the cap. So we have a smaller hole for the light to go in. And you can see the direction of the light is even more precise. So you really know where the light is coming from. Remember, I'm moving the light, not the eye itself. Okay, now let's turn the lights on back. Switch is somewhere over here. It's hard to tell when it is dark. All right. So three first stages, a flat surface, a pocket, and a pocket with a cap. Now, next level of this evolution will be represented by this. So we have a model made from a plumbing pipe. Here is a small hole for the light to get in. Somewhere over here, we have this layer made of a baking paper. So all the light that will go through here will shine on this part over here. And this whole thing here is just to block the light from the other side. So when we look inside of it, we only see this surface that light is shining on. And of course, at the very end, we also need this, a magnifying glass, something that will help us to see a good image of something. But now, a time for a question to you. And the question is, how do we call the light-sensitive layer of a human eye? And you can go with A, macula, B, retina, C, cornea, or D, iris. How do we call the light-sensitive layer of the eye? back to the darkness. Because we are preparing, or I'm preparing for the very, very final moment of my part. We'll now see what would be the view through this thing when we get a very small hole for the light to get in. And because I need both of my hands, I will mount it over here. And I can see that you are getting the right answer. B, like retina. That is the part of a human eye with all the light sensitive cells. The iris is the black thing, the black part of your eye. It is actually a hole in your eye. The light goes through your iris, shines on the retina, and you can see things. So now let's put the camera in front of this pipe. Because we have a very small hole, it is very dark image, but we are able now to see shapes. They are blurry, yes, they are. We cannot tell exactly what are we looking at, but we can know that it is moving up or down, left or right, closer or farther from us. So an animal with an eye like this, with a very small hole, would see quite good shapes. But if we want to see, for example, like us humans, we need also a lens and something that will clear the view. So I will put now the lens, this magnifier glass, in front of our retina. And now we can finally see our predator. The view is, of course, upside down, but that's a story for another presentation, I think. So back to the studio, the evolution of the eye, brief evolution of the eye. Thank you.
Yeah, thank you too, Tomek, for your demonstration. And you have a very adorable predator in your flat. And I want to, yeah, that's it. And I want to ask you about some questions, but we have technical issues here in our studio with sound. So I will ask you right now.
Okay.
And your title is that you are a science busker. So I want to know, what does it mean exactly, the science busker?
A busker is an English word to describe a person performing on a street. For example, a juggler, a street artist, or something like that. And the science busker is someone that performs science experiments, for example, on streets. You use like simple things, like a rubber duck, to talk about something. You can use, basically you could use this thing on a street because people can look inside of it. You can approach them with science, give them a look around, show to them how it works with the magnifier glass. And that's it. A science busker, a street performer, a person performing science. It is a very good way of performing science, for example, on festivals, when you can move around the festival, around people, and approach them with science.
All right, that sounds amazing. Thank you really for your demonstration of the evolution of eye. So thank you very much, and I think that we can go to the another performer.
Thank you.
Another performers who are going to join us are from Greece. Here our friend from
Thessaloniki.
Our, yeah,
from Thessaloniki, from noisy Thessaloniki.
But Your noises, sorry, I forget about the name of your science center. Sorry about that. So here's our friend from Noises Science Center, Elena. So hi to sunny Greece.
Hello, we're very happy to be with you tonight.
Yeah, we're happy too. The Noises Science Center is located in a beautiful place called Thessaloniki, as we said. If my information are correct, the Noises are going to have 20th anniversary this year. Is that right?
Yeah. And we opened doors in yes, more or less, yes.
Yeah, that's quite impressive because Vida is only 6-year-old. So you are older.
No. We opened the doors on 2005, so it's not quite 20 years. We have a history before then, so we can every day.
But at least you are older than
yes,
us,
we are a lot
you have more
older
experience.
Than yep.
Yeah. But now let's look to the video with Maria and Petros, who are your colleagues in Science Center.
Yes, Maria and Petros will give us a great video about and explain how things fall and what happens if sometimes and why sometimes things do not fall the way we expect them to. So we have to see what they have prepared for us and talk about it later.
Okay. So let's see.
Yep.
Hello, everybody. I'm Maria.
And I am Petros. We are at Noises in Thessaloniki, Greece.
Petros, to be honest, I was really looking forward to this day.
Okay.
Because we're going to do something pretty interesting.
Maria, I have been super anxious as well, as today we're going to drop stuff and see what happens.
What do you mean? Things fall and that's it? Or it's not?
Is it? And first of all, why do things fall?
Someone long ago had already explained it quite well. And as I can see, you have the same study object.
Dear Isaac, and long before him, Galileo certainly knew how to observe things falling and make the most of it. But let's concentrate on our own things falling. Fortunately, not on our heads.
Okay. We have placed on our bench this as a guide. So we make sure that all the things fall from the same height.
Okay. We take the object we're going to drop, which is this wonderful blue rubber ball.
I love blue.
And we simply let it fall.
Okay. The ball falls downwards. But why?
Maria, things generally move when forces act upon them. And in our case, the main force acting upon the rubber ball is the force of weight or the force of gravity with a downwards direction.
Well, to be exact, there is another force acting on the ball.
Okay.
There is the air resistance.
Yeah.
And it is opposite to weight.
Exactly. But this force is so small that we're going to pretend it doesn't exist. So it's just weight, which is the pulling force between Earth and objects on Earth or at a distance from Earth.
And as we consider that the air resistance is off, we can say that the ball is free falling with an acceleration equal to g, the so-called gravitational constant.
Excellent. But let's get rolling.
Okay.
Will the same thing happen if we use a plastic tube and let the ball fall through it?
Okay.
Let's see.
Once more, the ball falls down towards two bench.
Okay. Was it the same time?
At the same time, I can say.
Does the same thing happen with all tubes?
And now you're getting tubular, but
yes,
okay. Let's change tubes and try dropping it through a copper one.
So it's made of copper. Okay. Whoop. It dropped on the bench. Okay. And as we can see,
at the same time.
Exactly.
In all three cases, we had the same time, and it's reasonable because we had the same object.
falling from the same height
And with the same air resistance, we choose to forget about.
Okay. So, should we try with something else?
Yes, yes. Let's try something. What will happen if we have a magnet?
A magnet?
Yes, a magnet.
Is it just any magnet?
No, this is a very powerful magnetic sphere made by neodymium.
Quite powerful indeed. Straighten the thing out. Okay. So, wait a minute. It seems much heavier as well.
Yes, it really is.
Should we wait just to be sure? Excellent. Let's try first with the blue rubber ball. Okay, 14 grams. And now the powerful magnet. 64. Much heavier. So, Maria, it actually is heavier than the blue rubber ball, and time to let the magnet fall as well.
Once more, we have the same falling behavior at the same time.
So, the fact that the magnet has a much greater or a greater mass does not affect the fall as Galileo had already pointed out. The falling time in free fall depends only on the height and the acceleration g. And in our case, they both stay the same.
Hold your horses, cowboy.
Okay.
Why is that?
We said before that gravity is the pulling force between two objects. One of them being Earth, which is huge and, more importantly, massive. So it doesn't actually matter if we drop a wonderful blue rubber ball
or a neodymium magnetic sphere.
Exactly, or even an iron anvil. But let's leave cartoon physics for another time.
Okay. Now let's try to drop it through the plastic tube.
Exactly. Same thing.
What if we use the empty copper tube?
Seems like you're giving me a hint. Let's try.
Whoa.
Whoa, indeed.
Once again?
Let's do it again.
It took a little more time to fall.
Exactly. So it must have moved slower.
This means that something messed with the force of gravity.
Another force. And this force resists weight, makes the magnet move slower, and it must have come out of nowhere.
I wouldn't say out of nowhere. It doesn't sound scientific.
Okay.
And we wouldn't want to disappoint dear Isaac.
Yeah, the apple.
If not dear Lawrence, Faraday, or Lenz.
Okay, I get it. Neodymium is a magnetic material.
Yes.
And so must be copper. So it's the magnetic force. Ta-da!
And tanan. Copper.
Yeah.
It's not a magnetic material.
Okay.
But it's a good electricity conductor.
Okay. That's the key word. Now I get it, and you and all your cryptic references to Mr. Lenz and Mr. Faraday. They both help form the law of electromagnetic induction.
Say it again.
The law of electromagnetic induction. Da, 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 da. So, what actually happens is this. Thank you, milady. So, as the magnet moves through the tube, so do the electric charges within the tube or along the tube.
Okay. Movement of electric charges means electric current or electricity.
And whenever there's electricity around, there's always a new magnetic field being formed.
So, we have the magnet.
Okay.
And its magnetic field
exactly
moves.
And so do the electric charges along the tube. They move as well.
Which then create new magnetic fields.
And each of these magnetic fields create a new magnetic force. And the coefficient, or better, the combination of all these magnetic fields resist weight and make and cause the neodymium magnet to move slower.
I have a question.
Go ahead, shoot me.
Is this magnetic force stronger or higher than gravity?
Did you or anyone see the ball going upwards?
Nope.
Okay, so it's not stronger than gravity, but it's strong enough to mess with gravity.
And can we only play with copper tubes? I mean, does it work with any other material?
That's a really nice question, and I would be spoiling all the fun if I said yes. We can actually use any material which is a good electricity conductor, but is not magnetic. Do you have anything in mind? Maybe?
Like aluminium.
That sounds like a pretty good
Because
idea.
here,
Yeah.
I accidentally have this really thick aluminium tube to play with.
How accidental to have such a thick aluminium tube. Okay, go ahead first. Okay. Give me. I want to play as well.
Ta-da.
Okay, nice. Should we try with both? Yeah, let's do it. Whoop. It's like juggling with physics. Okay, so Maria, things do fall, but not always as we would expect them to. Sometimes materials interact or mess with each other in such a way that new forces come in play and we end up with pretty awesome results.
But I'm having fun with science.
Exactly. So, from me and Maria, we bid you farewell from Thessaloniki and we join scientific forces with everybody. Cheers.
Bye.
So wonderful video, Eliana. Thank you for that. Now I think we can wait for enough answers from viewers. Some of them just came here.
I can
But
see
meanwhile-
that, yes, a lot of them have already answered. Yes, please. I can
Yeah.
hear.
But meanwhile, let me ask you about something. We can give our viewers some space to put comments there. It's my bad, but I never been in your science center. So what is unique about noises?
The unique thing about noises is, of course, the fact that it is the first science center that we had in Greece. So opened in Noises in Thessaloniki, and it was very popular till now. Now there are some other science centers smaller than ours, another city in Athens, of course. But the thing with Noises is that it has a very beautiful and special building. The facilities are very new and very the people want to come and see us, not only for the things we saw them, but for the building itself, that it has a history from the ancient Archimedes, and with his idea about taking some lever and make the earth to go up, and so is the shape of our building. So this is one of the things that makes it special, is the building, and of course all these activities that anyone can take part in when visits Noises. We have a large techno park, it's the name, it's the interactive area, the interactive area exhibition, and you have a lot of interactive exhibits that is very popular for all ages, and a lot of other activities run in all over the year. Of course, now with the COVID situation, we didn't have a lot of things to do with live in live with the people that cannot visit us, but we try to have an online presentation with our website and our social media. So that's why we're very glad to be here with you tonight and join.
All right. So when we will be visiting Greece, we will visit also your science center. So
it will be very glad to see you.
Yeah.
Yes.
And
I've been there. I've been in Vida. I have been I visited your science center. It was really great. I loved it.
Yeah.
And then a lot of your colleagues there, and I'm very happy to see them.
Yeah, some of our colleagues were there in your science center as well. Yeah, but I think that we can look now for some comments.
Yes, I'm very
answers.
glad because I can see that we have correct answers. They, I think they all guessed that if we use a gold tube, then we could have phenomenon. Of course, it is the correct answer because gold is a material that has the two properties that that has to be in order to have the magnet fall down and slowing it down while falling. It is a material that is a very good electrical conductor, and of course, it's a not magnetic material. It's something like copper. And if we could use other tubes, also we could use maybe a silver tube or a tube from carbon or a tube from zinc. So all these materials have these two properties that makes them special when we want to observe things falling down through them.
All right. And do you have some gold tube?
Of course not. I
No,
wish I
that's a
had one
shame.
in my house, but I don't. Do you?
No. I don't own this. I don't own any golden stuff. Indeed.
Maybe a ring.
I own
Okay.
only the paper tube.
I think the paper tube cannot work like this.
Yeah, I think so. So thank you for your participation.
Thank you very
I
much.
think, yeah, welcome. And I think that we can move to the other performer.
Yes, with pleasure.
So let me welcome our next performer, that is Anya from Slovenia. Hi there, Anya.
Hello.
Hello. So Anya, we already know that you are a PhD student at CERN, because that you had some before that you had some experience with science shows in Slovenia in Hiša Experimento, yeah.
Exactly.
But I want to ask you more about the CERN, because for a physicist it is the one of the most famous places on Earth, I guess, minimally for me. There comes some Nobel Prize winners from the CERN. So do you want to get the Nobel Prize someday?
That is a very tricky question. And I have a too long answer to that. So when I studied physics, my idea was, of course, to once become a physicist to get a Nobel Prize. But then I figured out that a Nobel Prize, they don't really come that often. You have to be really lucky and really, really good. So at one point I decided that if I go and teach physics, then maybe I have a bigger chance of being thanked when someone gets a Nobel Prize. And I don't really care if the Nobel Prize is mine or of one of my students or one of the people who watch my show. But as long as I know that, that person saw me and maybe I inspired that Nobel Prize, that's the win for me.
Yeah, that's a nice idea, yeah. So, all right, Anya, you are going to show us some experiment with superconductors, yeah. So I think that you can go on, the screen is yours.
Perfect, thank you. So actually, I'm gonna continue from what you just saw, and I'm gonna try to show you, well, not really the golden tube. I found one here. It used to be on my finger, so the one like this. But even if I take a magnet and throw it through, I think it's not enough. We will need something better. And even though the gold is a very good conductor, it's not a superconductor. So a superconductor is just like gold, just like copper. Well, it has a property just like copper, so they can conduct electricity. But you know, just like heroes and superheroes, there's a hero and they're pretty good at what they do, but the superhero is, of course, it's better, right? It's the superhero has to be better. So if I take a material that's called a superconductor, well, that can be a superconductor, something like this, then maybe we can see also some super cool effects. However, if I take this tube, I still have it here, if I take the tube, I take the magnet, and I throw it through this tube. 3, 2, 1. Nothing really happens, right? And that's because this superconductor only becomes super under very certain conditions. And these conditions, well, they are very, very close to Switzerland here. It has to be really, really cold. But just cold, like 0 degrees, is not enough. What I actually need is a super cool liquid. Here it says Stickstoff because we have it written in German because Switzerland has 4 different languages. One of them is German. And here it says Stickstoff, which in English would mean nitrogen. Actually, here inside I have liquid nitrogen that boils at minus 196 degrees. Yeah, you heard that right. It's almost minus 200 degrees Celsius. So it's an extremely, extremely cold liquid. So I will now try to cool this tube down with this liquid nitrogen. You can almost see also on camera the liquid moving slightly. That's because it really starts boiling when it comes to contact with something that is on room temperature. So different things have different boiling points, and liquid nitrogen has, of course, a very low one. So as soon as this stops boiling, we know that the tube is actually cold enough. So now I will take this tube carefully, hold it like this. Well, first I have a question for you. If I cool down this cylinder, this tube, and I throw the magnet through it, what do you think will happen to this magnet? And I would like to ask the video team if you can put the question there. So how fast will this magnet fall through the superconductor tube? Will it fall faster than in air? So in air it falls like this. So very, very fast. Will it fall the same speed as in air? Will it fall slower than in air? Or will it not fall at all? So which one do you think will happen? So we know that this is a superconductor. It conducts electricity way better than the copper pipe before did. So something might be different, but it might also be the same. And we have no idea what to do. I will wait for a few more comments from you. I can see that, some of you are saying that it might go slower than in air, or, yeah, Oliver there was brave and he said he'll go directly with the option D so that it will not fall at all. No, Frederick, I think it will not explode, but just in case, maybe I will put this on. Okay. Mateusz also says, let's be crazy. I hope you are ready to be crazy. I will now hold this tube, stand up so you can see what I'm doing. So the magnet falls really quickly in air if I don't know how to hold it right. And now this time the tube is already warm. Okay. Come on, magnet. Magnet. No, let's do it with the hand. Are we ready? 3, 2, 1. Wow, can you see that? Let me cool it down a bit for you as well. Can you see the magnet is actually stuck? It does not fall through. As soon as the tube warms up, of course, the magnet will fall through. But when the tube is cold, the magnet stays in place. It stays on the top of the tube. So this is because of the special condition that happens inside this tube. So this tube is a superconductor, and it becomes superconducting only when it cools down. That's why we call this a special state of matter. So when we talk about state of matters, usually we talk about a solid, a liquid, and gas. But this one is one of the ones that we usually don't talk about, but there's plenty out there. We have superconductors, we have plasma, etc., etc. And superconductors can be very, very, very useful. But of course, the tube is only one way to show what a superconductor can do. Another way of doing this is by having, well, you know, a disc plate. This is a regular disc plate, and it's made of a similar, well, of the same material as the tube before. So it's made out of a ceramic that becomes superconducting when we cool it down. It might actually be easier if I just take this one because we have more liquid nitrogen here. So this thing is now gonna stick to the surface. That's the first thing that's gonna do. And now it's gonna cool down in here. And when it cools down, it will get a very special property that we call superconductivity. And of course, we know that through this disk, we cannot make the magnet fall, right? The magnet won't fall through this. There's no way that it will happen because it's solid. Although it's superconducting, it's still solid. Nothing can go through it. But once this cools down enough, what we can do is we can put a magnet on top and see what happens. If it's going to be anything like it was before, well, the magnet will start misbehaving. See? Every time I want to drop it on top of this, it starts misbehaving, and it is pushed away. Not kidding, I'm not throwing this away. It's really misbehaving a lot. But this doesn't matter. So now I always put it upside down. And you would say, of course, because magnets, you know, when you put them the same side and the same side together, they will repel. Let me try doing it upside down. Let's see what happens now. With a regular magnet, if this would be just a magnetic field, we would see that, of course, they would go together. But here, you can see it actually pushes it up and away. So superconductors actually behave in a way that they expel any magnetic field. They throw it out. They just don't want to do anything with magnetic field. They hate it. Unless they're a very specific type of a superconductor. And for this, I'm gonna show you a different experiment. And I will need to move my camera, so you will not see me anymore, I'm sorry. But you will see this fantastic little train. So we made a train out of with a 3D printer. It even has a nice smiley here. So this train, inside, it has a superconducting plate, the same one as we did see just now. So now I'm going to put it on two tiny plates, and I'm going to cool it down again. And because this is going to be cooling down for quite a while, I have plenty of time to explain actually what is happening inside these disks as well. So because superconductors are such good conductors, whenever we come close with a magnet, we have inside these superconductors basically an electric current that goes around. And this electric current then acts like an electromagnet. That's why it pushes the other magnet away. If I just go with a plastic plate next to it, nothing will happen. But when I move a magnet next to it, then things start to happen. But what is happening with the train at the moment is that this train is on a track. So you can see this track, and this entire track is made out of regular magnets. So that kind of magnets that we saw before, they are just put around on a track. And we are cooling this train down now. And while it is cooling down, of course, we have the same hate towards the magnets, but they kind of learn to love each other as well. So they kind of don't want to be together, but still they stick together a bit. So they're basically socially distancing, the same way as we do now during these COVID times. Okay, and our train is now ready. I will just cover it up, show you on camera how it actually looks like. Ta-da. Okay, and now let's take these plates out. You don't need the plates anymore. Look at the train go. And this train will continue to go in circles until air resistance slows it down, because there is no other resistance at this point than, of course, the air resistance. There's no traction because it is on a tiny air pillow. So it really is traveling around on an air pillow. And if we go like this, we can see it from afar, traveling really above these tracks. It's starting to shake now. That's because, of course, the magnetic field on the track is not completely perfect. That's why it starts shaking, because it's like, I don't like all of you guys, but some of you, I tolerate. Of course, as long as this superconductor stays cool, we can use it as, of course, we can see it in the chat as well, kind of like a hovercraft. But the same principle is actually used in maglevs, so in the super fast trains that we hear about in Asia. But superconductors itself are also useful for making another thing go in circles like this. And it's not a train, it's actually what trains are made of. At CERN, we use superconductors to make the smallest particles of matter that build an atom, so protons, not really the smallest, but one of the smallest, go around in circles, and that helps us do our research. Well, the train is still going. But I think it's gonna get to its final station, and so does my small part in today's live stream as well. Thank you very much for watching, and I'm looking forward to any comments that you might have. Back to you, Vida.
Yeah, thank you, Anya, for this experiment. It was a super cool experiment, as I can say. Yeah, and I think that liquid nitrogen is always good choice for a science show, because right science show should have experiments with liquid nitrogen, I guess. So, thank you, Anya, and I think that we can move on. On every VIRUScience broadcast, you can see Vida's main performers, but for today's broadcast, Aleš is technician and Janet is director of this whole show. I have one interesting fact, both of them. They are joined together through marriage. So these two guys are responsible for this event, and they are heart of our VIRUScience crew. And yesterday they grabbed a camera and shot a video experiment with Heron's fountain. Enjoy!
This experiment works by joining two pressures, hydrostatic pressure and atmospheric pressure. Here, the tube is full of water, and inside hydrostatic pressure is created in this lower vessel. Here is the second tube. There is only air in this tube, which transmits atmospheric pressure into the upper vessel and pushes it to the water surface. As a result, the water leaves the upper bottle and drains down.
And when the upper bottle will be empty, we could change the bottles. Heron's fountain works again.
Hi dear viewers again. For those who just start watching us right now, this is online broadcast called VIRUScience. In this broadcast we are focused on today's topic, join. Because there are performers joining together from all around the world. Don't be afraid to join us and write some comments on the experiment so the experiment can stand out. And now the next performer. So our next performance is another guest the local guest from Czech Republic. It is Sven from VIRUScience Center. Hi Sven.
Hello.
Hello there. So Sven is our leader of program department in VIRUScience Center, but I found that you were also a leader of Moravian Army. More precisely, general of Moravian Army. Is that true?
Yes, it was kind of a fun battle between the Swedes and the Moravians, you know, like a reconstruction of the 30 Years' War where there was a siege of Brno and we had big paper shields and we threw paper balls at each other and everybody made fun of me because I'm Sven.
All right. So it's really amazing. It was some role-play game, yeah?
Oh, yeah. Basically, we just wanted to kill the other army. Yeah.
All right, all right.
Yeah, that was our role.
That's a good thing. Nice one. And now I prepared one question which is more related to your job. And what last experiment really amazed you?
Oh, okay. What last experiment really amazed me?
Yeah. Is there any?
Yeah, well, I was really amazed at one thing which our colleague did when he was trying to show electron microscopy by evacuating a big chamber and showing some stuff in that.
All right.
I was quite amazed at like the idea. It wasn't like a real experiment, it was a metaphor, but I really loved that.
So maybe for next VIRUScience you can prepare it.
Oh. Okay, I'll be thinking about that. Thank you.
All right. So I think that is enough talking, and stage is yours.
Thank you very much. Today, a colleague gave me a cake, and it's beautiful. I'd really like to share it with you, so I'll come a bit closer, you know, and actually it looks really nice, but it seems that the cake is completely made of sugar, which is quite normal, I guess, because cake is usually just different forms of sugar put together, disguised as other stuff like flour. But basically it's just sugar. And it's important because most of what our brain actually consumes is sugar. And how do we actually get the energy from the sugar? Is by burning it, by recombining the sugar. But I'd like to look at the actual sugar molecules. Okay. Okay, here's the sugar molecule. This is actually a molecule of glucose, right? It has 6 carbons, 6 oxygens, and 12 hydrogens. Actually, this isn't glucose. This is, it's sucrose. It's actually 2 of this put together, but we'll just make it simpler. This is what actually our brain needs, what it eats. And how do we get the energy out of it? Well, we have to burn it. And what do we burn it with? We burn it with oxygen, of course. Yeah. So, I don't know if you actually see it. It's hard to see, but this is very fragile. It really almost falls apart, and it would like to recombine with something else. So, when I eat the sugar, it gets into my stomach, then it gets into my blood stream, then from there it gets into my individual cells, and the cells, they're always hungry for sugar. They need a bit of insulin to get inside, but at the end, they eat up all the sugar, and they have to get also some oxygen, right? And then the atoms recombine, and at the end, you have a happy cell who then just blows out carbon dioxide and water. And the carbon dioxide we breathe out, and the water we sweat out or we pee out, I guess. So, yeah, then we have a lot of it. And we have the energy. And that's how we actually run. And by breaking up the glucose, we actually have to put in a bit energy. You know, to break up something, you have to take it apart. That takes energy. But then, when it starts to recombine with the oxygen, actually this happens. Okay, that wasn't what I wanted to show, but can you hear it? When the bond is made, when the 2 atoms snap together, the energy which we can hear, which we hear as a sound on the microscopic level, that's the energy which then is released. So energy is actually released when bonds are created, and you have to put in energy to break the bonds. So, and do you know how much of these joining happens every second? I'll tell you, a lot. Actually, every second we recombine within our bodies, on average, about the number of molecules of sugar, which is the same as the number of sand grains on Earth. And throughout the whole day, you recombine and join molecules in the number which is roughly on the order of the stars in the observable universe. So we do quite a lot of work without actually knowing. And I'd like to see how it's done. So I'd like to see how the sugar is burned. So, I think I'll start with a flame. Should I take glasses? Maybe it will explode, so perhaps some glasses. Okay. It doesn't want to burn. It just melts and turns brown, caramelizes, but it is not burning. Do you see it? It's not black. And it's hot, actually. Okay, So we need something more. And it's actually quite good that, you know, that the sugar just doesn't burn spontaneously upon contact with oxygen, because then my cake would just burst in flames and I couldn't eat it when I want. So normally you have to have some kind of catalyst. And for here we can use kind of a really easy catalyst, which can be just ash. Here I'm having a wood splinter and I'm trying to put it on fire. Yeah. Have you turned off the fire system? We'll see in a while, okay? Now, once this stops glowing, I'll have a small piece of ash. Stop glowing. Stop glowing. It's stopping. Okay, okay. Now, I'll put the small piece of ash onto the cube. Stick, 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 stay there. Okay. Now I'll try to light it once again. And this time, I hope that something will happen. And I'm not sure whether it will actually work or not. I'm just hoping. And I can see it from here. I don't know whether you can see anything. So I'll try to come up a bit closer. Okay, one more time. Because what actually happens, although very inconclusively at this stage, as I'm sure, you can see that the cube actually is burning with a very faint blue. Okay, it's gone out. So basically the carbon should lower the activation energy, and on the same temperature as before it just melted, it should now actually burn. But you know, the big block of sugar, it might be too tight for actually proper combustion to happen. So it's much better if we will grind it into very, very fine powdered sugar. And I've taken the liberty also to light a whole bucket full of these splinters and put the ash inside so that we have plenty of catalyst in. And yeah, and one more thing, because I want to ensure that it will have a lot of space, you know, for all the gas to get in. I've put a special ingredient which you also put into cakes to make them fluffy. Do you know what that is? That's baking soda. Yeah, it's natrium hydrogen carbonate. Yeah, probably I've pronounced it quite wrongly, but it's baking soda. And when you put it into the oven, you need to add a source of heat. So I'll actually, you know what this is? Yeah, it's alcohol. And yeah, so I'll put it a bit around, not onto the sugar itself. And the brown stuff around, it's actually sand, so that the alcohol may properly soak in and then provide the source of heat. And while this will happen in a very short moment, I have a question for you. This 1 cube of sugar weighs approximately 2.6 grams. And I'm wondering how much energy is stored inside. Now, to have an imagination of how we could measure this energy, imagine an athlete who is providing a top performance. Someone like Usain Bolt, let's say. And Usain, you know, he's on the starting point and he's concentrating with all his might, and in the next few seconds, in 1 second, he will have to go up to speed. So that's the maximum power his muscles will start making. And my question is, if he kept on having this maximum performance, how long could he run at this maximum metabolic rate from just 1 cube of sugar, 2.6 grams? So in seconds, how long would he be able to run at maximum performance from just this 1 cube of sugar? Okay, so please put all of your tips and guesses into the comment section, and I will proceed with our experiment. I will try to put it on fire. Okay, it seems to be on fire. I don't know whether you see something happening. It might be happening. And I'm really curious about, what do you think, how long would Usain last on this 1 cube of sugar? Now, those of you who are not really familiar with Mr. Usain, he's a rather, big guy, athletes who run sprints. They're quite massive, so he has about 94 kilograms. Okay, and somebody actually measured how much performance his muscles make when he's starting. And I'll tell you, it's actually 140 watts per each kilogram of his body weight. So he's like a very, very old light bulb eating away 140 watts of each of the kilograms of his 94 kilograms of weight. Now, what is happening here, I'm not sure whether you see it or not, we are starting to build up some strange shapes. Okay. That's not what I actually expected, but yeah, we'll see how long this lasts. We can clearly see that the sugar is burning, but it's not really fast. There's not much heat going off. Okay, so I've seen a lot of tips, some very, very small time scales, some very, very large time scales. Okay, 30 seconds, 20 seconds, there's a lot of different, 20 seconds, okay. Now, I think that you're almost in the right ballpark. It's not hours, and it's not minutes. So actually, Mr. Usain, if he would to eat this single cube, he would last for 30 seconds at his maximum performance. Okay, so, and I see that very close was Andrzej and Radka. So, I'm not Usain, but I can get the same energy, I just will have to keep on talking for a bit longer to get it out. Okay, and this experiment will probably go on here for 5 more minutes, and we'll see what happens, but, I would really like to see that energy released at a much higher rate. I really can imagine how Mr. Usain, when he's starting, when all that energy from the sugar is, just exploding into the muscles and they keep on moving. So I'd like to see a much faster reaction than this. And evidently having a catalyst and having the sugar very well ground is not enough. So what we could improve is the access to oxygen. We need more oxygen. He's breathing really, really, really fast. And although, like 100 meters, we could almost run without breathing. It's completely an anaerobic metabolism. But, I'm not that good, so I would have to breathe, from the second on. So I need more oxygen. So how could I add more oxygen? I could bring in a flask of oxygen and put it on there, but then I could maybe end like the movie Martian, when they improvised something at the end. So perhaps we could make us an improvised device. Do you know what this device is? It's called a gas burner for camping. It's a very specific device. I'll try to light it on fire. Ah, it actually works. I didn't expect that to happen, but it does. Okay. So now we have a source of heat to actually start the reaction, and we have here a flask full of very fine powdered sugar. And what I will try to do is actually get a bit more space, and I'll try to dissipate all this fine ground sugar into the flame. And we'll see how fast the reaction actually goes, hopefully. Prepare the fire extinguishers! Okay, that wasn't bad. So, I'm not sure, but I think that this is about the rate at which Mr. Usain would be able to. Okay, I have just half of the flask. I've already emptied the half other. So this is about the rate at which he could, at top speed, use up that sugar within his muscles. And that's about it. And I hope that you'll have enough energy by joining the carbons with oxygens at home.
All right, thank you very much, Sven, about your sweet experiments. I will remember you when I go for a run.
Okay,
yes.
Please do that.
Yeah, so thank you very much. And I think that we can move on to another performers. And last but not least is Diane and Chris from the USA. So hi guys.
Hi.
Hi to the USA. You both are high school teachers of physics, and you try to teach physics in an interesting way. I believe we are going to see some of it. But first, I have one quick question on Diane and another to Chris. Yeah? So Diane, we found that you are teaching food science also.
Yes. Yes.
Yeah, so that sounds really amazing. So what is your favorite science phenomenon in cooking?
I think, I guess looking at the solubility of sugar and how that affects like candy making, and then also one that I really liked was freezing point depression, using sugar to make things like sorbets and ice creams. So obviously on the sweet side, like Sven, but that's what I really loved teaching when I taught food science.
Oh, that's sweet. And Chris, we know that you have really playful mind and you play with physics toys and you quite like the tinkering. So is there some science toy which you love the most?
Science toy that I like the most?
Yeah.
That's a very difficult question to answer. In fact, I'm going to give you a sneak preview of what we're doing. I love this science toy, my little car, but you'll see later.
All right, we will see.
I think his favorite toy is actually the sound wagon that you put on the record player and it plays. That's
You think that's my favorite?
I do think that's your favorite.
Oh, so thank you. So thank you guys. No more talking. Let's go to your experiments. Screen is yours.
Okay.
Thank you.
Thank you. Hi, today we're going to talk about what happens when you take two surfaces and you join them together. So we're just going to start with something really basic. Now you may notice Chris and I don't have a laboratory. You're in my house. So we just pulled some things off the shelf, literally, for this demo. So we're just going to join these two books like this, except we did it already here. Now,
Do you think we can pull these apart?
I
Diane?
think we can give it a try.
Okay. Ah!
Oh my goodness, he's pulling me across the floor. So our first question is, what force do you think is responsible for making it really hard to pull these two books apart?
We're getting some good answers.
Yeah. So what force? A, is it gravity?
B, friction.
Tension?
Or magnetic.
Which force is responsible for keeping these two stuck together? Hi, Maya. All right. Great job, guys. Yes, it is the force of friction. And so when two surfaces come in contact with each other, we often have a frictional force between those two. And in our experience, people always talk about friction in a negative light, trying to eliminate it, reduce it, it messes up your experiment. But today we want to have a little fun with it.
As I mentioned, one of my favorite toys is this little car. And it's battery operated, as you can see. And I like it so much that I brought two of them. Now, let's see how they compare when we have a race. Oh boy, they didn't want to go, Diane. There they go! I hope you saw that they stayed together, that they're almost identical in their speeds. Now, we're going to try something else with friction. I've got an empty tube here that we'll place between the cars, and the only reason for that is we don't want the cars climbing over each other. The reason for this setup is we're going to have a push of war, not a tug of war, but a push of war between the cars. Now the question is, will one of the cars win, or will it be a stalemate?
Hey,
look,
that's pretty good. Woohoo!
So they're balanced.
All right. So, Chris, is there anything we could do to make one car win the battle?
Perhaps. We are talking about friction, aren't we?
Yes.
Have an idea. I've got a ball here that's pretty heavy. Now, the question is, when we turn the cars on and we know that they're balanced, what will happen when I put the ball in one of the cars?
Well, let's give it a try. Wow!
Whoa!
Wow, that's so good! That's pretty awesome. That is pretty awesome. So, our next question to you is, what causes the car with the ball in it to win? Because obviously the car with the ball in it won the battle each time. Is it A, it now has more energy?
B, it pushes harder on the table and creates more friction.
C, it has less friction.
D, it changes its mass.
We'll give you a second to think about that one. Why did that car win?
Oh, we have some good answers, Diane.
Everybody's saying B, Chris. It pushes harder on the table and creates more friction, but wouldn't more friction slow it down?
Not in this case. It actually helps it push off the table. So it's like in a tug of war, it's the team that pushes off the ground the hardest. This just happens to be a push of war.
Very nice. Nice job. That's a really nice one.
Okay.
So friction increases when two surfaces are pushed harder together. Is that what we're saying?
That's what we're saying.
So try this. So take your hands and just lightly rub them together. And if you listen, maybe you can hear the friction.
Oh yeah, I can hear it.
Can you hear it?
Oh yeah.
Now what if you pushed them even harder together? Did the same thing. Can you hear? It gets louder, right? There's more friction in that.
But Diane, there's something else going on there.
What?
My hands are getting warmer.
Shut up.
Shut up, they are.
Shut the front door. We are getting heat. So friction often creates heat. Matter of fact, that's why most mechanical things have fans in them to get some of that heat out of there, or they just melt. So,
do you have something that illustrates that, Diane?
If only we could come up with a way to show that friction creates heat. Well, I think I have something. I was making a smoothie the other day, And, you know, we don't have superconductors or liquid nitrogen, but we have water and smoothies. So this is just some water in my smoothie thing. And let's just take the temperature of our water right now. So.
22.1 Celsius.
Okay, so right now the water temperature is 22.1 Celsius. I'm gonna let the blades beat up the water a little bit, cause a little friction for about 30 seconds. Talk amongst yourselves. All right, that should be good. We've had a little issue here. We can't remember what the original temperature was. Can somebody put it in the chat?
Help us, please.
Help us. What was the original temperature?
Oh my God.
Well, we're at 24.2. I think it was 22.4.
I believe it was 22, and now it's jumped up to 24.
So just 30 seconds in the smoothie. No heat here, okay? This didn't warm it. It's not, this machine's not hot at all. We were able to raise the temperature of the water, okay?
2 degrees.
2 degrees, just using friction. Wow.
Oh boy, here's the question now. Since friction caused the water to increase in temperature, we're wondering if it's possible to even boil water if we have enough friction. So over here, I've got a copper tube mounted in a board, that's all.
Now give us a second, I'm gonna move the camera.
And I'm going to put a little water in the tube. Not much. Okay, we're gonna wait.
Wait.
Oh, we just lost, there we go.
There we go. Okay, hold on, moving the camera.
Okay, I'm gonna put some water in the tube.
Hold on, Chris, I just want to get a little bit closer to you here.
Okay, I've just put water in the tube, and I've just got a nylon rope, and I'm going to wrap it around the tube.
Okay, now you got to watch carefully here, folks.
Now, this may take a while, so you may want to go get a drink or go to the bathroom.
Not that long.
No, it doesn't take that long.
Come on, Chris.
I'm working.
Come on, baby.
Come on. Now, you know, Diane, we may need a little help from our audience.
Yes.
So, along with us, would you please say, boil, 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 boil.
Oh, boil.
Come on, come on.
Come on, baby. You're moving the whole table. Come on.
Come on.
Come on. Oh, no.
We're taking the table into the other room. Oh, there it goes. There it goes. There it goes.
Well, that is pretty awesome. That is pretty awesome.
Okay, so we didn't know if that would work or not. Obviously, we're very pleased that it did. So we've seen that friction is a helpful thing. It helps us move. And also, a byproduct of friction is heat. So we really appreciate you inviting us. We've had a great time. Thank you very much.
Right. Back to you, Evita.
Yeah, thank you too. You were amazing, simply. We all in the studio are laughing right now. So thank you very much. I don't know what I can say more or what I can ask you. So I think that our broadcast is coming to the end. And now I really want to thank you, dear viewers, that you were watching us and put some comments there. The next broadcast, VIRUScience, is going to take place on 3rd of June at 8 p.m. We will be happy to have you join us again. topic of next broadcast are going to be outdoor, but next time it will be in Czech again. So sorry for viewers abroad. At least you can train your your Czech language skill here. And now some last words from our performers. So Dan and Chris, do you want to say us something for goodbye?
Thank you so much, everyone, for showing up. We hope you had a good time. Just remember, science is fun and friction is fun.
Thank you so much for the invitation. We've had a wonderful time. Bye-bye.
Yeah, we do. Thank you very much. Bye-bye. And Anya, do you have any last words for the viewers?
Thank you so much for joining and thank you so much for inviting me. This was extremely fun and I definitely learned something now.
Yeah, welcome. Thank you too. Tomek, do you have some message for us?
A message? You changed the question. I was going to thank everyone for joining and for the invitation. The message, peace and love, and rock and roll. And science. Yeah, science, woo!
Science rocks, yeah. So thank you, Tomek. Eliana, any message to the viewers?
Yes, I would like to thank you all for being with us. It was a very nice experience and I hope it will be not the only one. I hope another one and another one and another one join can be together.
Okay,
Thank
we
you.
hope so. Thank you.
Bye-bye.
Too. And what's up to you guys, Sven and Jaffa? Any last comments?
Well, I hope that you will exceed my experiment, and as you have seen, we can get electricity if we join large enough surface for such weak electrolyte as normal water, as there are very few ions or ions only from the hard water. So I'm looking forward for you to exceed me and making some huge battery with distilled water where there are even less ions.
Okay, thank you. Sven?
Don't eat sugar. And if you have to, then go out for a run.
All right, bye guys for now. So thank you all guys, all the performers for this wonderful experiment. I really enjoyed it and I believe that every viewer enjoyed it as well. So see you next time, and for now everyone in our crew come here. Just everyone, our cameraman Simon, go. Just come here. Yeah. So this is our whole crew of VIRUScience. And yeah, we are really not much space here. So goodbye, good night, good afternoon, good whatever part of day you have. Bye.